Welcome to Vandenberg Air Force Base in California and our pre-launch briefing for the GRACE follow-on mission. I'm Steve Cole from NASA Communications. We're here today to tell you about the GRACE follow-on mission. That stands for the Gravity Recovery and Climate Experiment mission. Follow-on because this is the second of the GRACE missions that we've flown. We're all set to launch tomorrow, May 22nd at 12:47 p.m. Pacific time. We'll be sharing the ride into space with 5 Iridium NEXT communication satellites on a SpaceX Falcon 9 rocket. GRACE Follow-On is a joint mission between NASA and the German Research Center for Geosciences, or GFZ. We have 5 panelists for you today to tell you more about the mission, so let me introduce you to them. Our first panelist will be David Jarrett, GRACE Follow-On Program Executive in the Earth Science Division at NASA headquarters. Frank Webb, GRACE Follow-On Project Scientist at NASA's Jet Propulsion Laboratory. Frank Fleckner, GRACE Follow-On Project Manager at the German Research Center for Geosciences. Phil Morton, GRACE Follow-On Project Manager at the Jet Propulsion Laboratory. And finally, Captain Jennifer Hayden, Weather Officer for the 30th Space Wing at Vandenberg. After our presentations, we'll have questions from the media, both here in the auditorium, on the phone lines, and on social media. If you're watching on NASA television, you can ask a question with social media by using the hashtag AskNASA. So we're ready to begin. Dave, over to you.
Good morning, and thank you for joining us. We're very excited today to discuss the GRACE follow-on mission with you. GRACE will continue the legacy of the original GRACE mission, which ended just not long ago last year, bringing us 15 years worth of exciting data and making many new discoveries. NASA Earth Science program studies Earth as a complete system. In this animation, you can see that NASA currently has 17 satellites in orbit, measuring everything from gases and clouds in the atmosphere to rainfall and soil moisture to land surface change and the water cycle. Tomorrow, GRACE Follow-On will be the 2 new kids on the block to continue to measure the mass of the Earth's mass changes of the Earth's system, from the storage of water and aquifers to the changes in ice sheets and glaciers. And without the help of our international partners, the Germans, we wouldn't be here today. GFZ is contributing the launch vehicle, mission operations, the laser radar reflectors, and the optical components of the laser ranging interferometer technology development experiment. NASA is providing the 2 satellites, microwave instruments, the accelerometers, and the electronic components of the laser ranging interferometer. This kind of cost sharing brings more bang to the buck, and euro in the case of GRACE Follow-On, to the American and German people, as well as benefiting researchers from around the world. The next image shows NASA's current fleet with missions involving our international partners highlighted in red. This type of collaboration is very important to us because we're able to share the cost of the missions and thereby enabling us to do a whole lot more for less. It's a win-win situation for everyone because all countries benefit from the wealth of data that we gather about our complex, ever-changing world and the impacts it has on our daily lives. GRACE Follow-On is unique. Most of our satellites use imagers that collect light reflected from the surface or the atmosphere. For GRACE Follow-On, the instrument is really the 2 satellites together as a system. The critical measurement that's made by GRACE Follow-On is the very small changes in distance between the 2 satellites as they orbit the Earth. And these changes are caused by the pull of gravity as it changes very minutely, caused by different things. Before we get into discussing exactly how those measurements are taken, Frank Webb will describe the science of the mission and its impacts on our daily lives.
Thanks, Dave. So I just want to start out by saying, just saying a little bit about the GRACE mission, which we're the follow-on to. So GRACE was really a revolutionary mission for us understanding the water cycle and how the climate behaves and the trends which are taking place over the last, 10 or 15 years. And it did this in a very unique way by, making measurements of how the mass gets redistributed on the surface of the Earth. And this was a view that we didn't have before of the water on Earth. We're able to see how water has moved from different parts of the Earth by actually measuring its mass, which is not something you see with your eyes. It's something you have to feel with the satellite system. And we'll hear a little bit more about that later. So if we go to the first animation, which shows some of the results from the 15 years of GRACE measurements. This is a map of mass trends seen by GRACE. And as this animation goes forward, it's pointing out several regions of the world, both on the land and in the ocean and the ice sheets, where with GRACE we were able to detect things like loss of ice mass from glaciers, ice sheets, Greenland, places like that. Be able to see storage of water on land in areas where there was floods, or depletion of water on land where there's large aquifers and we've been pumping water out, or there's been droughts where we've been pumping out more water than has been accumulating. We can also see from the GRACE data the actual amount of mass that actually went into the oceans. Not just measuring the sea level, but actually measuring the mass within the ocean. Because the sea level is a sea level rise. It has basically two components. It's the mass which goes into the ocean, the volume change from that, but also the volume change from thermal expansion of the water. So there's those two things which actually total to make the whole sea level rise. And by measuring with GRACE the mass change, we actually measure how much of that is water in the ocean, how much is actually heating of the ocean and thermal expansion, which is very important for understanding climate processes and predicting the future of understanding where they're headed. So if you go to the next animation, I'll look in a little more detail for some of the things shown on the previous chart. And this just shows mass loss in Greenland. So you can see on the left, you can see Greenland. On the right, you can see what's the monthly measurements of mass change, the monthly measure of water mass change or ice mass change in Greenland. And you see, there's a bit of a seasonal cycle there. But you see overall, Greenland is actually has been losing mass over the last 15 years. And it's a little bit, it's fairly linear. It's about 281 gigatons per year of mass loss. And with the GRACE data, we were able to see actually where that's coming from. It's not just that it's coming from Greenland overall. You can see that mostly in that figure, it's coming from mostly the southern part of Greenland. And that's led to other studies where we're looking at how the influence of oceans in accelerating that mass loss, so warming of the oceans around Greenland, and how they interact with the ice or in the fjord, the glaciers which pour into the seas. So that's a very significant finding there, and the amount of mass being lost, as well as the fact that mass was being lost. When we first started GRACE, it really wasn't clear what the sign of the mass change in Greenland was. Was mass gaining ice or gaining mass, gaining ice, gaining water, gaining snow, or is it losing it? But it's pretty clear from the 15 years of GRACE data that it's been losing mass. Now, if you start the next animation, so in that animation, I said it's losing 281 gigatons of water a year. And this animation is just because a gigaton is kind of a strange unit for people to understand. A gigaton is a cube of water a kilometer on a side, and this just shows it here in graphical form next to the Empire State Building, just for reference. That's 1,400 feet high or 0.4 kilometers high. So that's what a gigaton is, and so Greenland loses 281 of those a year. Now, if we go to the next animation, this is an animation that is of Antarctica. Another place where you have a large ice mass, which is changing as climate is changing and evolving. And this again, you see, the loss of mass from Antarctica on the monthly scale. And you can see, as it's every month is counting out from the GRACE data. And you can see in the colors, you can see where it's being lost. You see it's mostly being lost in the Western Antarctica. There's actually a little bit of gain in Eastern Antarctica, and that is interesting, though overall, from the standpoint of the mass balance of Antarctica, the amount of water that's being, and ice that's remaining in Antarctica is losing more ice than it's gaining. And here it's 120 gigatons of water a year. And combined, Antarctica and Greenland account the amount of mass being lost. That's about 400 and something gigatons a year, and that's equivalent to about a millimeter or more of sea level rise per year, just coming from those two ice masses. And this is something that we've learned from the GRACE data for the last 15 years. It's something that, with GRACE Follow-on, we will be extending this data record so we can better understand, if these trends are continuing and better understand, what the drivers of them are, because it's very important for us to understand, with the data we collect at NASA, one of the very important things about the data for society is that it helps inform us and helps us understand these processes so we make informed decisions. The next animation, so it's not just about ice or mass loss from that. This is mass loss from water on the surface. This is an animation from Western United States, which shows a mass loss from basically the large aquifer in Central California. So we use a lot of groundwater in California, and we had a drought a few years ago, and during that drought, California lost water weight, as farmers and agriculture pumped out more water to meet the needs that weren't being met by the snowpack in the mountains or the rainfall. And with the GRACE data, we could see clearly that it was losing weight, and that was coming from this region of California where we have our large aquifer. And at the end of that series of GRACE measurements, which was sort of the end of the GRACE time series, we had a large rainstorm, and there was some recovery in the amount of water in the ground. It remains to be seen, since GRACE ended in 2017, how that recovery goes forward. But in a year, once GRACE launches tomorrow, we'll start getting data, and we'll have about a 1-year gap, and we'll be able to see how much of that water that fell, as precipitation in California, actually stayed in the ground and went into storage, or you can better understand how much actually ran off and went into the oceans. It's important for us to understand the whole water process there. And so, that's just a little bit about the science of that we've learned from GRACE, and this is the science that we will be continuing with GRACE Follow-on, and to better understand these trends, and understand if these trends are just short-term trends or short-term variability or longer-term trends related to sort of our evolving climate. And with that, I'm going to hand off to Frank, who's going to explain a little bit more about how the measurement actually works.
Sure, Frank. Thanks. So this I would shortly explain by an animation, which shows you that GRACE Follow-on is a constellation of 2 satellites separated by about 220 kilometers. And the measurement of this inter-satellite range is the most critical data on GRACE and GRACE Follow-on. It is a function how the mass is distributed on ground. So if mass changes on ground, like in aquifers or melting glaciers or in the oceans and so on, you see it immediately in a range change, which we measure very, very precisely by a microwave tracking system with a precision of about 1 micrometer. That is about 1/10 of a human hair over the distance between Los Angeles and San Diego. So this instrument is used as a, let's say, primary objective to continue the time series which we have started with GRACE and to continue with GRACE Follow-on. But we have also another secondary objective with GRACE Follow-on, which is explained on the next figure. So to improve the spatial and the temporal resolution of our Mars observations for future GRACE-like missions, we will fly a technology demonstrator called laser ranging interferometer. So due to the shorter wavelengths of the laser ranging interferometer, we will be able to observe a separation change at least a factor of 10 better than we do it with a microwave instrument, which is a prime instrument on board of GRACE Follow-on. And the laser ranging interferometer is really an excellent example of our great partnership between the US and Germany. So for the LRI, the cavity and the electronics are provided by our US partners. And we in Germany have provided all the optics, like the optical bench assembly, a triple mirror assembly, and others. And the partners in Germany are the Albert Einstein Institute, SpaceX, and DLR, the German Space Agency. And we have implemented the laser ranging interferometer in a so-called racetrack configuration. As you have seen, the satellite was already filled by all the nominal instrumentation, by the tanks inside of a satellite. So we had to choose a way how to route the laser beam inside of a satellite. And for that, the triple mirror assembly is most important, to route it by 180 degrees back to the opposite satellite. But we have also another secondary objective, which is explained in the next video. So here we use the so-called radio occultation principle, which was first developed for the CHAMP satellite, launched in 2000, a satellite launched by my institute, GFZ. And we have not only a prime antenna on top of the satellites to perform the navigation of GRACE follow-on, but we have also another secondary antenna on the backside of each of these satellites, which observe the signals between low altitude GPS satellite disappearing or coming up over the horizon of the Earth. And these signals are altered by refractive effects within the atmosphere. And this we can observe and derive temperature and humidity profiles, which we provide to the weather services on a 24/7 basis with a time delay of less than 3 hours. So therefore we have installed a ground station in Spitsbergen on at the near of the North Pole, and use this station to fulfill the stringent requirements of the weather services. We have another instrument on board of GRACE follow-on, and we had it on GRACE, which is a laser retroreflector provided by my institute. And we shoot from a network of about 20-25 globally distributed ground stations. You see here an example, the Potsdam ground station. By a laser to this laser retroreflectors, receives the beam back from the reflector, and from the two-way travel time you can derive the orbit with millimeter precision, and this serves for an independent control of the GPS-derived orbit of GRACE and GRACE follow-on. How mission operations will be performed after launch is shown in the next video. GFZ has subcontracted the German Space Operations Center in Oberpfaffenhofen because they have a lot of experience from the GRACE mission. They are running the Mission Control Center in Oberpfaffenhofen, which you can see here in the video. They operate 2 ground stations in Weilheim and Neustrelitz. And in Neustrelitz we have also the raw data center, which collects all the downlink data and provided to the science data system for further processing. And finally, we will use the station which I have introduced with the radio occultation for GRACE. This is a primary downlink station on Spitsbergen, so therefore we have now every orbit, every 90 minutes telemetry data from the satellites, which helps to improve the checking of the health status of GRACE follow-on. And finally, I would like to mention we are here for the launch. It will be performed in 26 hours from now. And therefore, we have signed a contract, a rideshare contract with Iridium, which is shown here on the next video. We will use a Falcon 9 here from Vandenberg Air Force Base, together with 5 Iridium NEXT satellites, GRACE follow-on top of this 5. We will be separated about 11.5 minutes after launch. And the 2 satellites will then be separated into 2 opposite directions and flying towards south. Und mit dem würde ich gerne weitergeben an meinen Freund und Partner Phil Morton, sitting beside me.
Thank you, Frank. I'm going to give you a little more information about the satellites themselves. We have 2 scale models here. They are 1/10 scale. So think of the actual satellite size as about the size of a sports car. As they mentioned before, one in Los Angeles and one in San Diego. That's how far apart they're flying typically.
they have a unique shape. We took great care to make sure that the satellite size and shape was identical to GRACE, because we want to make sure that we have a continuity mission and that we try to do everything we can to collect the same kind of data that we took on GRACE. And there's some characteristics in the shape that help with the aerodynamics of their orbiting. We want to put the two satellites in orbit. We want to do as little as possible to keep from perturbing them. We let them float. And we want them to react to the gravity field and the changes in mass, and then measure those very finely, precisely measured distances of a micron. In order to do that, the business end, one end has the dual K and K band microwave signal that we use to is the primary instrument to measure the distance between the two satellites. And then you'll see two ports here that these are the laser baffles. The laser, kind of think of it as a racetrack. There's one laser that's a master that we cycle that beam around between the two satellites. The outside of the satellite is covered with solar arrays. It's kind of a sleek look, but this provides our power. There are some cutouts here. These are the star camera baffles. We use star cameras and a precision GPS antenna on top to map very precisely the location of these little changes in the distance between the two spacecraft. And then again, as Frank mentioned, on the back side of the spacecraft, we have a radio occultation antenna. And that's what we use to look at GPS signals moving through the atmosphere and use those to measure humidity in the atmosphere. And also underneath, there's an S-band boom. When it's deployed, it deploys early on in the mission, and that's what we use for radio transmission to the ground stations. I have a video here to kind of give you an idea of the inside of the spacecraft. It's quite compact, but you can see as it was put together at Airbus. It's quite complicated inside. We took essentially the GRACE design, did upgrades for avionics, various bits of equipment that we could no longer get because of the 15-year lifetime, which improved our avionics, our electronics. In the very heart of the spacecraft, you can see in the video here, is an accelerometer that's very sensitive. We use that to remove gravitational effects. And that piece of equipment is aligned very precisely with the triple mirror assembly and the star cameras, so that we make sure there's a particular reference for all the measurements that are made that's in the heart of the proof mass of the accelerometer. So you can see that whole assembly being lowered into the middle of the spacecraft. It's kind of in the heart, in the very center of mass of the spacecraft. Once we were done with environmental testing, we transported all of our equipment, the satellites, out here to Vandenberg. This was last December. And the Air Force helped us unload and move all of our equipment. It was quite a process. We brought the two satellites, our multi-satellite dispenser, and all of our ground support equipment. We moved everything over to the Astrotech facility here, did our functional checks, our fueling of our nitrogen tanks, battery charging, and then we moved over to the Harris facility, and you can see a time lapse here of us lifting the satellites and putting them on the multi-satellite dispenser. So we had teams from Madrid, Spain, from Germany, JPL, all working together here to get these satellites put on the satellite dispenser, properly mounted, so that we can separate absolutely as we need to. So it was quite a bit of work. Once we were done here at Harris, we packed up that whole stack, we call it the stack, and we transported it over to SpaceX, where we started doing our integration activities with Iridium. I've got a couple of images here I'll just go through and just kind of give you an idea of the work that was done there. It was quite complicated and very interesting. Here you can see us removing the top of our shipping container. The two spacecraft are mounted on the multi-satellite dispenser, but they're protected under a protective cover. Next image, please. You can see us now. We've uncovered the satellites. We made sure that now they're stepping towards getting more and more flight ready as we remove protective covers. We lift the whole assembly up and we mount the base of our multi-satellite dispenser onto this adapter ring. This was built by SpaceX to mate us directly onto the dispenser for the Iridium stack. If you go to the next picture, you can see here below is the stack of 5 Iridium satellites, and we are lifting our stack assembly and then dropping it on top, and then we will mate it to the top of the Iridium stack. Next image. And again, you can see here the combined set of payloads, the Iridium stack on the bottom and the GRACE satellites on the top. So this is quite a spectacular view of what the satellites look like. If you go to the next image, this was a very interesting piece of procedure that we had to execute. We lifted our stack and the Iridium stack together and then moved the whole thing over to this adapter, the payload adapter, that is what mounts on the top of the second stage. So you know, an interesting, very delicate and very precise movement of all the equipment to line it up and get it ready to go for launch. Next image. And you'll see here the final stack as it is. Now, the current status, all of this now is encapsulated in the fairing. We finished up that work end of last week and over the weekend. The fairing now is been tipped horizontally, and the whole assembly then mounted on the second stage of the rocket, which is in the hangar over at SpaceX, and should be rolling out this morning. So we'll do our final testing over there today and finish our checkouts and get ready for launch tomorrow. So very exciting time. I have another video here. I just want to talk a little bit about what happens after separation, give you an idea of what's going to happen right after we separate. We come away from the dispenser. About 50 seconds after we separate, we have a boom deployment. You see a little bit of an animation here of it. And then about 5 minutes after that, we start our attitude control system up. We start pointing the S-band booms towards the Earth. We want them to fly in this kind of a configuration. The spacecrafts are moving slowly apart and heading towards the South Pole. It takes about 23 minutes before we get to the first ground station, which is McMurdo in Antarctica. And when we pass over McMurdo, we'll do a very quick check on both satellites to make sure we get telemetry, do a dump of some data, check on their health very quickly. And we have every expectation of getting both satellites. If for some reason we only get one, then about 45 minutes later, we come over another ground station at Svalbard that's up toward the North Pole. And then we have essentially passes every orbit so that we'll continue to get more and more data and check on the health and welfare of the spacecraft. So we're all set, all the ground stations, ground ops, everything's ready to go for tomorrow. So we're looking forward to the big day. And now Captain Hayden for the weather briefing.
Thank you. So I'll be going over and speaking to the weather and what we can expect tomorrow for day of launch. For those who don't know, here in Central California in May, we tend to see this daily pattern of fog and low stratus in the morning, what we refer to as our marine layer. And in the afternoon, that breaks up gradually and then is replaced by some gustier winds due to our sea breeze. Now currently, however, we're seeing a slight disruption to that typical pattern. We have a late season low pressure system that has moved in and really dug into Central and Southern California. What this low pressure system has done is simply thickened our marine layer up. It'll make it a little bit more stubborn to burn off tomorrow, and has yielded some drizzle this morning. As we look to the satellite, we can see abundant low and mid-level clouds as they circulate counterclockwise around that low pressure center as it makes its way over California. As the satellite imagery continues to loop, you can see that these clouds will continue to push east as the day progresses. What this means for tomorrow's forecast, the high pressure won't quite have had time to build in just yet, so our marine layer will continue to be elevated for launch day, much like we're seeing this morning. This will result in cloudy conditions at T0 from approximately 800 to 1,600 feet. However, visibility will be unrestricted, which is good news for launch viewing, and temperatures will be in the mid to high 50s. Surface winds will be slightly elevated, out of the west at 8 to 12 knots, which will drive our overall probability of violation for T0 to be less than 10%, with that only constraint of concern being ground winds. What that means is that we're assessing a less than 10% chance that weather conditions will be a factor at takeoff. As we move to the scrub day forecast, the low will continue to shift further to the east and will finally allow our high pressure to settle back into place and return us to that more typical pattern as I mentioned earlier. Daytime heating will scatter out our marine layer and lead to just a few clouds and unrestricted visibility at T0. Temperatures will increase slightly as we get more heating in the day to the upper 50s to low 60s, and winds will turn out of the west and decrease slightly to 7 to 10 knots. What this will do is drop our POV, or probability of violation, to 0% for our scrub day. We have no areas of concern for weather. And that is all for weather. Back to you, Steve.
Okay, thank you, Captain Hayden, and to all our panelists. We'll start with questions now. As a reminder, for those watching on NASA TV, you can post a question to social media using the hashtag AskNASA. And we have reporters in the room, reporters on the phone line. Please, if you're stating a question, give us your name and affiliation. I think we have some on social media, so Caitlin, we'll start with you.
Sure. Manish on Twitter asks, what type of research will be done from this mission and how would we benefit from it?
So I'll take that question. So the type of research that will be done for this mission is mostly related to climate and hydrology. We'll be able to understand the trends that we've seen from GRACE, how those trends are continuing, and whether or not, the factors which are driving those trends, whether they're due to short-term variability or sort of longer-term climate trends. And that, of course, is very important for us to understand, a number of things about the Earth system. One, for example, is just understanding how we manage our water resources. Because with GRACE, GRACE and GRACE Follow-on, we're able to see, depletion of aquifers in the ground and the rising of sea and the addition of water mass to the oceans, and those are very important for society as we try to manage our resources.
Okay, I guess we can keep going with social media questions.
Planet By on Twitter asks, how identical are the GRACE FO twins?
They are absolutely identical. The only difference is they have an ID that separates them from our communications to the ground, but we built them and took great care to make sure that they're absolutely identical.
Hi, Michael Baylor for NASA Spaceflight. I was wondering if the laser works as expected, then it would be better than the microwave instrument, I believe. So will then that be used instead, even though it's a secondary mission, or will you still use both? How will that work? Thank you.
I think I can answer that. We will, of course, rely first of all on the microwave instrument. That's clear. We want to follow on the mission. Yeah? It's a technology demonstrator. We will try to switch on the laser ranging interferometer quite soon. And we can also operate both instruments in parallel. So we will make inspections, if you want, of both instruments during our in-orbit checkout phase and so on. And then we will see how it operates. We can derive gravity fields from both kind of measurements. And if we really would see that the laser ranging interferometer behaves as it was designed, I would see there's no doubt to switch to the laser ranging interferometer. That's clear.
Okay, we have a question here in the room.
Roger Eckert, Mad River Union newspaper. This is a little more mundane question, but curious about the rideshare arrangement. This isn't like you just stick out your thumb and hitch a ride on a rocket launch. So who talks to who and how do you get together on this?
Maybe that's a question to me. So part of, let's say, our contract with NASA is that Germany is responsible for providing the launcher. And we have signed this rideshare contract because it is part of the cost sharing between Germany and the US. We also share our costs with Iridium. It's of course nothing what happens every day, but we have experienced a very, very good partnership with Iridium and SpaceX, and we are totally confident that we have a successful launch tomorrow.
Okay, I think we have another question in the room right up front here.
Hi, Anthony Weiss, Mad River Union. I have two questions. I read in the media pack that the satellites will change orientation a couple times through the mission, and I was wondering about that. And then why the solar panels have the little voids in them, the little red marks on them. Thanks.
Yeah. So the first question, when the spacecraft are moving in orbit, one end of them is bombarded by atomic oxygen. And so it's this kind of a strategy of ours to reduce impacts to the end, the material on the end. And so about halfway through the mission, we will swap positions, and so then the other satellite will take some of that, the atomic oxygen impact. And then depending on how long we go, and we hope to go a bit longer than our 5-year mission, we'll work our strategy for best times to do the exchange. This is just a maneuver that we do similar to the maneuvers where we do station keeping between the satellites and try and keep them about 220 kilometers apart. With respect to the voids in the solar arrays, are you talking about these little tiny marks, or are you talking about these
the red dots.
Yeah, this is just an interpretation on the model of how the solar panels are laid down. There's a certain number of cells per string, and so it's more of a manufacturing issue. There's some gaps between some cell blocks as they're placed on the spacecraft, and so it comes out to not perfectly covered, but again, it's just a matter of how it's laid down on the cells.
Okay, we have a question from the phone lines from a reporter at The Verge. Go ahead, please. Identify yourself.
Hi, this is Alessandra Potenza at The Verge. I was just wondering if one of us could explain how the distance change between the two satellites results in a measurement of the mass change down on Earth.
I think I can answer that. So we observe this distance measurements together with other observations which have been highlighted by Phil, for example, from the accelerometer. We measure all the non-gravitational measurements due to air drag or solar radiation. And we invert all these measurements during orbit determination. We solve a large linear equation system with about 10,000 unknowns over 1 month to solve for a representation of the gravity field for 1 month.
Okay, we have another question on the phone lines from Spaceflight Now. Go ahead, please.
Hi, thanks for taking my call. Could one of you please give me the target orbit when you separate from the Falcon 9, apogee, perigee, inclination, and is there any maneuvering the satellites have to do to reach their final science orbit? Can you walk me through that commissioning and when you anticipate starting the science mission? And secondly, could one of you provide the total cost of the Grace follow-on mission with both the German and U.S. contributions? Thank you.
I'll take the first part of that question. We launch into 490 kilometers, plus or minus 10. So we're approximately 500 kilometers in altitude at 89 degrees inclination. When we separate, we're angled down at 30 degrees, so one comes off a little higher altitude, one comes off a little lower. This causes them to begin to drift apart. And we are injecting directly towards the South Pole at 89 degrees. So we don't do any particular maneuvering other than to get them in a safe state and get them nadir pointed on the bottom panel. and then we let them naturally drift apart over a couple of days until they get about the right distance apart, approximately 220 kilometers. And this is a very kind of natural process, and so we will just head toward the South Pole. It's a fairly simple a process that we go through. We don't do any particular maneuvering other than when we reach our distance, we do a station stop maneuver where we slow things down and try and drift at around 220 kilometers.
To answer the second part of that question, the NASA contribution to this mission is approximately $430 million, and I'll let Frank answer the question for the German contributions.
I can answer that clearly. It's about 77 million euro for all the German contributed items.
Okay, thank you. I guess we have another, let's see, another question here up in the front row.
Yeah, I was wondering how quickly the two GRACE satellites have to get away from the Falcon 9 second stage before it performs the second burn for the Iridium satellites. Thank you.
To look at the timeline, I think the state. I mean, once we separate, we start moving away, and it's I think about 2 minutes. But I have to check on that before they fire to move into their orbit. That's something we'll have to check.
Yeah, we can get you that information. We have another question on social media. Caitlin.
On Twitter, Mari Takahashi from Smosh asks, how soon will the data be collected and made available to the public?
Because I'll take that. So after launch, we have about a 90-day period of in-orbit checkout. And during that period, we'll be collecting, turning on systems, turning on instruments, getting the spacecraft thermally stable, and start collecting the first data. It takes about 30 days of data to do one gravity field. So during that 90-day period, if all goes as expected, we'll probably collect our first, couple of 30-day periods. And then we'll start generating gravity fields after that. So expect, the first sort of science fields to come, 90 days or so after launch, and then the goal is to have releases to, the science community about 180 days after in-orbit checkout.
Okay, we have another question in the room.
Roger Eckert, Mad River Union newspaper. For the original GRACE mission and the follow-on mission, were you expecting the information that you got? Were you planning for this, or were there any information there that was a surprise, that you found particularly useful?
So I like this question because I think the original GRACE mission was a competed mission through the NASA ESSP program, and it was a proposal that was written for it. And people ask this question a lot about what sort of surprises we had from GRACE. And we actually have gone back and looked at the original proposal, and almost all of the things we saw with GRACE were predicted to have been seen. We didn't know how much, but we knew that the mission would be able to sense mass loss, be able to detect mass loss from the ice sheets, mass gain in the oceans, underground groundwater mass changes in the solid earth from large earthquakes, and I think almost all of these were kind of predicted in the proposal and were seen. Now the sort of the part that wasn't in the proposal, of course, was how much those changes were, what they meant, where they were occurring, and how fast they were occurring. And those were really some of the really revolutionary parts or results from the GRACE mission. And we could see, for example, ice sheets, losing ice and losing mass, and we could see it going into the oceans, and then we could actually compare that with altimetry data and see how much actual energy, thermal expansion was taking place in the oceans, which is something that we were not able to see to discriminate those two components before. Also, when there was a period in 2011 when sea level sort of sea level rise slowed down a little bit and actually kind of went the other direction very briefly. And from the GRACE data, one could see, or we could see that even though the ice sheets were still losing ice at the same rate, sea level kind of slowed down, rising a little bit. And that was also seen in the GRACE data was that during that period, there was more water being stored on land. There was some heavier rainy seasons in Australia and South America, and that sort of equivalent of mass was actually going to storage on land very briefly instead of going into the oceans. And it was eventually, released in the oceans, and the rate of sea level rise, continued.
Okay, I think we have some additional questions on social media. Caitlin?
From Twitter, Ivan Carone of AFP asks, what other kinds of mass besides water may be detected by Grace FO satellites?
So I think so the satellites are are sensitive to all mass change around the globe, and we make measurements every 30 days, and so we see atmospheric ocean tides, solid Earth changes, water, ice, moving around. On the 30-day time scale, there are a lot of things which don't change very rapidly, and the solid Earth doesn't change very rapidly unless we have an earthquake. And for atmospheric mass changes, we tend to calibrate that out because we want to see sort of water. So we have some models based on atmospheric models. How much mass is in the atmosphere, so we can calibrate that out and really get down to sort of mass change from water in the ground, in the surface material, in the oceans, in the ice sheets.
Okay, let's see, do we have any other additional questions here in the room on social media? Okay, well, with no further questions, that'll end our briefing for today. Just want to remind everyone to tune in to our live launch broadcast. Starts tomorrow at 12:15 Pacific, 3:15 Eastern. And you can also follow along on the launch blog, which is online at nasa.gov/GraceFO, where you can find a lot more information about this unique and important mission to study our changing planet. Thanks for watching.